All right, let's really dig into this. Today, we're taking a deep dive into something that's, well, it's rapidly reshaping our digital and physical worlds. Artificial intelligence agents. You've probably heard the term bounced around, but what truly sets them apart? We're kind of moving beyond AI that just does narrow, specific tasks, into this new era with autonomous entities capable of really complex reasoning and action. So when we talk about an AI agent, we mean an active participant in an environment, pursuing goals with a remarkable degree of independence.
Exactly. And at their absolute core, whether they're super simple or incredibly complex, it all really boils down to this continuous cycle.
Hmm.
Sense, think, and act. An AI agent is always like gathering data from its surroundings, its environment, then processing that information to make smart decisions, and then crucially taking meaningful actions to get closer to its objectives. That fundamental loop, that defines their whole operation.
Okay, so to be super precise then, when we use the phrase AI agent, what exactly are we defining? Is it just a program or is there, more to it?
Oh, it's definitely more than just a program. Think of an AI agent as a software system, right? But one that uses AI capabilities to first perceive its environment, second, to reason about its goals, and third, to autonomously execute actions, to complete tasks for a user or maybe another system. And to really be an agent, a system needs to show some key characteristics. First up, autonomy. This is huge. It's the ability to operate, make decisions independently with minimal human handholding. It's not waiting for your every command.
Right, it does things on its own.
Precisely. Then there's reasoning. This is basically how they figure things out, using logic, using information they have to connect the dots and solve problems. They also need planning. So mapping out sequences of actions to reach longer-term goals. Kind of like a sophisticated GPS plotting out every single turn, but for potentially much more complex tasks. And finally, memory. Storing experiences, facts, rules. This helps them learn and informs their future decisions.
It's fascinating how generative AI, and especially these powerful foundation models like large language models, LLMs, they seem to be becoming the real cognitive engine here. Are they essentially the brain giving agents these abilities, understanding, reasoning, planning?
They absolutely are foundational, yeah. The engine is a good way to put it, but this is also where we need to clear up some common mix-ups. An AI model, like an LLM, is that cognitive engine. But it's not the whole picture. Models are kind of passive, right? They're trained on data, they recognize patterns, generate outputs when prompted. An AI agent, though, that's the active, goal-oriented system. It uses one or maybe even multiple models to think. But the agent itself provides the autonomy, the drive, and the way to actually act in the world.
Got it. So an LLM just sitting on a server isn't an agent, but an agent uses an LLM to do its job. That clicks.
Exactly. And that also helps distinguish them from what we usually call AI assistants. Think Apple's Siri, Amazon's Alexa, Google Assistant. Those are a specific type of agent, sure, but they're designed mostly for direct kind of reactive collaboration with a user. They wait for your prompt, then they respond.
Right. They do what I tell them.
Mostly, yeah. Broader AI agents, though, they often have a much higher degree of autonomy. They can proactively chase multi-step goals with very little direct command. Sometimes they might even kick off tasks without you explicitly asking them to, based on their goals and observations. And then you've got bots. These are really at the lower end of the autonomy scale. They mostly just follow predefined rules for simple, repetitive stuff. Very limited learning, if any. AI agents handle way more complexity, autonomy, learning, adaptation, much smarter. And for anyone familiar with older AI concepts, expert systems are different too. They were pretty rigid. Fixed knowledge base, lots of if-then rules. They didn't really adapt or learn unless someone manually updated them. Modern AI agents are much more flexible and dynamic.
That's a useful breakdown. So as you, the listener, go about your day, maybe interacting with different AI, pause and think about these distinctions. Does understanding this change how you see the AI around you? Is it just a tool or something more agentic? Now, here's a really practical question.
Yeah.
How do you actually design and analyze something this complex, like an AI agent? Is there a blueprint, a framework?
There is, actually, a really helpful one called the PEAS framework. It stands for Performance Measure, Environment, Actuators, and Sensors. It's a structured way, almost like a checklist, to nail down an agent's purpose, where it operates, and what it can do. Very clear.
PEAS. Okay, break that down for us.
Sure. P is for performance measure. This defines success. How do we know if the agent is doing a good job? It quantifies the desired outcomes. For an autonomous car, this would be things like safety, definitely on number one, avoiding collisions, speed, following traffic laws, maybe even passenger comfort. For an AI, handling customer support. User satisfaction scores, how quickly it solves the problem, the accuracy of its answers, that sort of thing.
Okay, P is performance. What's E?
E is for environment. This is the whole context the agent operates in. It could be physical, like roads, weather, other cars for that autonomous vehicle, or it could be digital, like a computer's file system, a network, or a database for a software agent. And environments have properties too. Are they static or dynamic? Discrete or continuous? Fully observable or only partially? These factors dictate how complex the agent needs to be.
Right, the world it lives in. Makes sense. A.
A is for actuators. These are the agent's tools for taking action, how it actually influences the environment. For a physical robot, this is pretty obvious. Motors, wheels, arms, grippers. For a software agent, it might be making API calls, changing entries in a database, executing a financial trade, sending an email. Those are its hands.
S must be sensors.
You got it. S is for sensors. These are the instruments the agent uses to perceive the environment, how it gathers raw data about its world. An autonomous vehicle. Cameras, LiDAR, GPS, microphones perhaps, a customer service agent. It senses by ingesting customer messages, maybe accessing CRM data, running sentiment analysis on the text.
What I like about P's is it seems to give us this common language. We can compare different systems using it. It probably helps make AI research more replicable too, right?
Mm-hmm.
And it forces designers to think carefully about safety and ethics by making them define what the agent can and should do and what it perceives. It feels like a governance tool as much as a design tool.
That's a great point. It absolutely functions that way. And if you step back, Pease really frames an AI agent as an embodied system, even if it's purely digital. The sensors and actuators mean its intelligence is grounded in interaction with a specific world. It's not abstract intelligence. It actually parallels biology. Organisms adapt to their ecological niche. It suggests effective AI agents are highly specialized, tightly coupled to their environment. And this idea even informs how some people think about reaching artificial general intelligence, AGI, through designing these whole organism architectures that interact richly with their surroundings.
Okay, let's shift perspective a bit. Look at this like an evolution. AI agents didn't just appear fully formed. They've built up capabilities over time. From really simple reactions to incredibly complex learning. It's like climbing a ladder of intelligence, isn't it?
It really is. We can sort of categorize them based on their capabilities. At the bottom rung, you have simple reflex agents. These are the most basic, governed purely by if condition, then action rules, based only on the current perception. No memory, no history. Think of a simple thermostat. If temperature below X, turn on heat. Or an automatic door. If motion detected, open. Basic spam filters work like this too. They're a big limitation. They're pretty useless in environments where you can't see everything or where things change. They only react to right now. They can get stuck in loops easily.
Okay, simple reflexes. What's the next step up?
That would be model-based reflex agents. This is a significant jump. They maintain an internal model, basically, a memory or understanding of how the world works. They can use their perception history to infer the current state of the world, even things they can't directly see right now. An autonomous vehicle tracking a car that momentarily goes behind a truck, that's using a model. Modern irrigation systems adjusting based on past weather. Advanced home automation. They're much more adaptable to partially observable environments, but they are still fundamentally reactive. They respond to the world as it changes based on their model.
Better, but still reactive. When do they become proactive?
That's the next level, goal-based agents. This is where we see a major shift. They don't just react, they actively try to achieve defined goals. They use planning algorithms. They can essentially ask themselves, what will happen if I do action X, and then strategize to reach a desired future state. Your GPS navigation app planning the best route is a classic goal-based agent, a chess-playing AI looking several moves ahead. Logistics robots planning how to retrieve items in a warehouse.
Okay, now they have goals. Can they get more sophisticated in how they pursue those goals?
Yes, that brings us to utility-based agents. These are a more refined version of goal-based agents. They don't just want to reach a goal, they want to reach the best possible state. They optimize a utility function. Think of it as quantifying satisfaction or happiness with an outcome. This allows them to make nuanced decisions, especially when facing multiple, maybe conflicting goals or dealing with uncertainty. An autonomous vehicle has to constantly balance speed versus safety versus passenger comfort. That's a utility calculation. A financial trading agent balancing expected returns against potential risk. Smart energy grids optimizing power distribution. They're aiming for optimal outcomes.
So they weigh different factors, and the top of the ladder.
That would be learning agents. Their defining feature is that they autonomously improve their performance over time. They learn from experience and feedback. They adapt their behavior, refine their internal models, maybe even generate new knowledge or strategies. Under the hood, they typically have several components: a performance element, the part that acts; a critic, which evaluates how well it did; a learning element, which figures out how to improve; and sometimes a problem generator, which suggests trying new things, exploring. They use all sorts of machine learning: supervised, self-supervised, and especially reinforcement learning. E-commerce recommendation engines that get better at predicting what you'll like, adaptive chatbots, game-playing AI like AlphaGo, those are prime examples of learning agents.
Okay, that progression makes sense. But it strikes me there's a crucial trade-off here. As these agents get smarter, more capable, more adaptive, doesn't their behavior become less predictable? Harder to understand why they did what they did? This sounds like the black box problem people talk about.
You've hit on a critical point. Yes, generally, as performance and adaptability go up, predictability and interpretability tend to go down. And that's exactly why fields like explainable AI or XAI are becoming so important, and why concepts like human in the loop or HITL oversight are vital for advanced agents. We want them to be powerful, but we also need to trust them and understand their reasoning, especially in high-stakes situations.
Right. Makes sense. Let's shift gears slightly then. What's the actual tech powering these agents today? What's really under the hood making all this possible?
Yeah, good question. Modern AI agents really rely on a combination of synergistic technologies. You can think of it as a tripartite structure, mapping back to that sense, think, act cycle. First, you have the cognitive engine. This is largely driven by large language models and other machine learning techniques. LLMs are often the brain, providing sophisticated reasoning, language understanding, and planning abilities. Machine learning more broadly provides the toolkit for training them. This includes supervised learning training on labeled examples, like a customer service agent learning from past successful interactions. Also, unsupervised or self-supervised learning, finding patterns in vast amounts of unlabeled data to get a really robust understanding of a domain. And critically, especially for business applications, integrating these models with existing systems, CRM, ERP databases, gives the agent a holistic 360-degree view for truly intelligent decision-making.
So the LMLs if think. What
Yeah.
drives the act part, the autonomy?
That's the second pillar. The engine of autonomy, which is primarily reinforcement learning, or RL. While LLMs give the agent the capacity to reason and plan, RL provides the mechanism for it to learn how to act effectively in its environment through trial and error. It's this continuous dance. The agent takes an action in the environment, observes the new state, and receives a reward or penalty. Over time, it learns a policy, a strategy for choosing actions that maximizes its total cumulative reward.
Trial and error. Learning from rewards. Makes
Well,
sense.
yeah, and a key challenge with an RL is the exploration-exploitation trade-off. Does the agent stick with actions it knows work well, exploitation, or does it try new things that might be even better, exploration? Think of it like trying a new route to work. It might be faster, or you might get stuck in traffic. Agents need strategies, like the epsilon greedy strategy, to balance this. RL is implemented using various methods. Some focus on estimating the value of states or actions, like Q learning. Others directly learn the policy, and some combine both, like actor-critic methods. Interestingly, actor-critic methods have parallels to how dopamine works in the human brain as a teaching signal. RL is absolutely instrumental for complex sequential decision-making tasks, like robotics, autonomous driving, or playing strategic games.
Okay, so LLMs for thinking, RL for learning to act. What about the sense part? How do they perceive the world?
That's the third pillar, the perceptual system. This is powered mainly by natural language processing, NLP, and computer vision. NLP enables agents to understand and generate human language. It's the backbone of conversational AI. It involves tasks like recognizing user intent, analyzing sentiment, understanding context in a dialogue. This relies on techniques like tokenization, lemmatization, and especially powerful deep learning models like transformers, absolutely essential for virtual assistants, advanced chatbots, any agent interacting via text or speech.
And computer vision, that's for seeing.
Exactly. Computer vision equips agents to process, analyze, and interpret visual data. It allows them to see the world. Critical tasks here include object detection, what's in the image, instant segmentation, where exactly is each object, and object tracking, following objects over time. This is indispensable for physically embodied agents. Autonomous vehicles use it constantly to see roads, cars, pedestrians, signs. Warehouse robots use it to identify, locate, and sort packages.
So it's really
Absolutely. What's crucial to grasp is that the recent explosion in agentic AI isn't because of just one breakthrough, it's the concurrent advancements across all three of these pillars: sense, think, act. An agent's overall performance is genuinely limited by its weakest link. If it can think brilliantly but can't perceive its environment accurately, it's not going to be effective. Future progress really depends on balanced, simultaneous advancements across the board.
That's a really important insight. It's the whole system working together. Okay, let's scale this idea up now. We've talked about individual agents. What happens when we bring a whole team of AI agents together? This brings us to multi-agent systems, or MAS. What's the core idea there?
Right, MAS. The basic idea is you have a system composed of multiple autonomous agents that interact with each other. They're decentralized. The principle is often to tackle problems that are too complex or too large for any single agent to handle alone. You distribute the problem across a team of specialized agents. Imagine breaking down a complex research project. One agent finds sources, another summarizes them, a third drafts the report, a fourth checks for quality. They collaborate.
So distributing the workload.
Exactly. Key characteristics include decentralization. Usually, no single agent is in charge of everything. Local views, each agent typically only has partial information about the entire system or problem, so communication becomes vital. And constant interaction, they need to communicate, coordinate their actions, maybe even negotiate or resolve conflicts to achieve the collective goal.
If they're like a team, are there different ways they usually organize themselves, like different team structures?
Yeah, there are common architectural patterns. You see network or equi-level architecture. Here, agents are basically peers in a flat hierarchy. Think of a collaborative team with no single boss. They coordinate amongst themselves. Then there's the supervisor or hierarchical architecture. This is more like a traditional org chart. A central manager agent orchestrates the workflow, delegates subtasks to specialized worker agents, maybe even treats them like tools it can call upon. And you also find hybrid or nested architectures that combine elements of both, allowing for really complex modular setups.
Okay, so they need to work together. How do they actually communicate and coordinate?
Communication and coordination mechanisms are critical. For communication, they need protocols. This could be direct message passing between specific agents, using APIs to request services from each other, or maybe writing to and reading from shared data structures, like a shared Blackboard or database. For coordination, there are different strategies. Task sharing, where tasks are dynamically allocated based on agent availability or capability. Results sharing, where agents combine their intermediate findings, or consensus-based decision-making, where they might use voting protocols or negotiation algorithms to agree on a course of action.
This sounds complex. What are the big challenges in getting this collective intelligence to actually work well?
Oh, there are definitely significant challenges. One is optimal task allocation. How do you dynamically figure out which agent is best suited for a given subtask, especially as the situation changes? Another is designing for robust reasoning and debate. How do agents effectively discuss, challenge each other's findings, and iteratively refine their collective understanding or plan? You don't want groupthink, even in AI. Complex context management is tough too, ensuring all agents maintain awareness of the relevant context from the overall goal down to the specifics of their current subtask and shared assumptions. And advanced memory management is crucial for the group. Not just individual memory, but shared memory. Things like a consensus memory for agreed-upon facts or an episodic memory tracking past group interactions and decisions.
You know, what's really striking as you describe this, these challenges in MAS design sound incredibly similar to challenges in human organizational design. Management science, basically. A supervisor architecture is like a top-down company. A network architecture is like a flat, agile team. Could this lead to something like computational management science, maybe even virtual companies run by agents?
That's a fascinating parallel, and yes, many researchers see that connection explicitly. The principles of effective coordination, communication, task allocation, and conflict resolution in MAS are deeply related to organizational theory. The idea of computational management science is very real, using MAS simulations to test organizational structures. And virtual companies composed of specialized agents. That's definitely something people are exploring, especially for automating complex digital workflows. It's a profound direction.
Okay, let's ground this a bit more. Can you give us some concrete examples? Where are AI agents making a real difference in the world right now?
Absolutely. Let's look at autonomous systems, where AI gets a physical body. Autonomous vehicles are a prime example, maybe the quintessential complex AI agent system. A self-driving car uses multiple agent types, model-based agents for perceiving the world, goal-based agents for planning the route, utility-based agents for making those split-second tactical decisions, balancing safety, speed, comfort. They heavily rely on computer vision, RL, sensors galore. Companies like Waymo, Tesla, Cruise are pushing this.
Right, cars are a big one. What else physically?
Warehouse robotics. These are often multi-agent systems, frequently using that hierarchical structure we talked about. Physical robots use computer vision to identify items, navigate the warehouse, pick things up, sort them. They coordinate to avoid collisions and optimize throughput. The impact is huge efficiency gains. There's a company, Sequoia Robotics. They reported boosting inventory identification speed by 75% and cutting processing time by 25% using their AI agent-driven robots.
Wow, okay, so physical robots. What about in the digital realm?
In digital interaction, the change is massive. Think about personal assistants, Siri, Alexa, Google Assistant. They're everywhere now. These are AI assistants, a type of agent using NLP to understand your voice commands, set reminders, play music, control your smart home devices. And moving beyond assistants, advanced customer service is being transformed. AI agents can now handle complex customer inquiries from start to finish. They use NLP to understand the problem, manage the conversation, access back-end systems, maybe check order status, process a refund, and only escalate the really tricky edge cases to a human agent. This automates a huge chunk of support work.
So interacting with us, what about behind the scenes in businesses?
Big impact in enterprise operations. Take supply chain management. AI agents are used for autonomous demand forecasting, analyzing real-time data way faster than humans could. They handle intelligent procurement monitoring, supplier performance, maybe automatically switching vendors based on preset criteria, and dynamic logistics optimization, constantly recalculating shipping routes based on traffic, weather, fuel prices. Uber Freight, for instance, uses AI agents to match available truckers with loads much more efficiently, reportedly cutting down those wasteful empty miles by 10–15%.
That's significant savings. Any other big enterprise areas?
Cybersecurity is another huge one. AI agents offer a critical speed and scale advantage needed for modern defense. Humans just can't keep up with the volume of threats. They're used for proactive threat hunting, looking for subtle anomalies in network behavior that might indicate an attack. For automated incident response, quickly isolating an infected machine or disabling a compromised user account to contain damage. And for building an adaptive security posture, learning from past attacks and adjusting defenses automatically. An AI agent system can monitor and analyze data from thousands of endpoints simultaneously.
It seems like the level of autonomy varies a lot, though. The customer service agent works with a human sometimes. The cyber agent needs to act instantly on its own.
That's a key takeaway. Autonomy isn't an on-off switch, it's a spectrum. It's a deliberate design choice based on the task's risk, complexity, and real-time requirements. A customer service agent is often designed to be more collaborative. A cybersecurity agent responding to a zero-day attack needs maximum autonomy and speed. There's no time for approval. And this directly highlights the critical need we mentioned: strong governance frameworks. These define the agent's scope of authority, its operating rules, what decisions it can make autonomously, and crucially, clear escalation paths for when human oversight or intervention is required.
It's almost like you need to grant them authority, like in law. Expressed authority for specific tasks, maybe implied authority for related ones, with clear boundaries. Okay, we've seen the power, let's get critical now. What are the real challenges, the limitations, the downsides we need to consider?
Right, it's crucial to have a balanced view. The benefits are compelling, no doubt. We talked about productivity and efficiency, automating complex tasks, 247 operation, freeing up humans. Accuracy and quality agents can be highly accurate, self-correct, speed-up processes. Scalability and cost savings, handling more volume without linearly scaling staff, reducing operational costs. And data-driven decision-making, leveraging vast data for better insights and strategy.
The challenges.
They are significant. First, unpredictability and control. Because advanced agents, especially those using LLMs, exhibit flexible, sometimes human-like reasoning, their behavior isn't always predictable. They might interpret instructions unexpectedly or exhibit seemingly irrational behavior or even reproduce subtle biases from their training data. This creates a real tension between wanting their powerful autonomy and needing reliable control.
How do you even test something like that?
That's the next challenge: robust testing and validation. It's hard. Because they learn and adapt, you can't just test them once. It requires continuous, comprehensive testing, monitoring them closely in production to ensure they behave as expected and to catch failures quickly. Building trust in these systems is a major hurdle, and it requires rigorous, ongoing, transparent evaluation.
What about security? They sound like powerful tools if compromised.
Absolutely. Security and reliability are paramount concerns. Agents often need deep access to sensitive data and critical systems to do their jobs, making them incredibly high-value targets for attackers. Plus, they're susceptible to new kinds of attacks, like prompt injection, where malicious inputs trick the agent into doing something harmful, or they might inadvertently leak confidential information they processed.
And they need good data, right? Garbage in, garbage out.
Fundamentally, data quality and availability is a constant challenge. An agent's performance is utterly dependent on the quality, completeness, and, crucially, lack of bias in the data it's trained on and uses for decisions. Bad data leads directly to bad outcomes. Then there's the practical integration and complexity. Hooking these advanced agents into existing, often older legacy business systems can be a massive technical headache. API compatibility, data consistency, maintaining performance, it often requires specialized expertise and can be quite costly.
And you mentioned LLMs can hallucinate. What happens when an agent relies on a hallucination?
That's a huge risk. Hallucinations and compounding errors. LLMs can sometimes generate outputs that sound plausible but are factually incorrect hallucinations. Okay. Now imagine an agent performing a multi-step task. If it hallucinates a key piece of information early on, say, gets a customer's account balance wrong, and then makes subsequent decisions based on that wrong info, you can get a cascade of compounding errors. The whole process goes off the rails, potentially leading to significant failures, and it can be incredibly hard to trace back the root cause to that initial hallucination.
This reminds me of technical debt in software engineering. Maybe we need a term like agentic debt. It's like the implied long-term costs of managing these complex, unpredictable systems. You get productivity up front, but you accrue this debt, the ongoing cost of governance, monitoring, security, fixing errors, mitigating risks. If you don't manage that debt, the interest payments, a major security breach, a huge business blunder caused by an agent could wipe out all the initial gains. It reframes deploying agents. It's not just about ROI. It's a complex strategic choice needing serious ongoing investment in governance and oversight. Maybe we'll see new jobs like AI agent auditor.
Agentic debt. I like that. It captures the ongoing responsibility perfectly, and it leads us directly into the ethical and societal implications, which are deeply intertwined with these technical challenges.
Yes, let's go there. Beyond the tech, what are the profound ethical and societal questions these autonomous agents force us to confront?
There are several critical areas. One of the most discussed is algorithmic bias and fairness. This isn't about algorithms being inherently biased. It's about systematic errors in agent models leading to unfair or discriminatory outcomes. The causes are often human. Biased training data that reflects historical inequalities, like an AI recruiting tool learning to penalize resumes mentioning women's chess club, flawed algorithm design, or using seemingly neutral proxies like zip codes that actually correlate strongly with protected attributes like race. The consequences are real and documented. We've seen examples in criminal justice systems incorrectly predicting higher recidivism for Black defendants, in healthcare with diagnostic tools being less accurate for minority patients, in financial services leading to disparities in loan approvals or interest rates. Mitigating this requires conscious effort. Curating diverse and representative data using bias detection tools, ensuring diverse and inclusive design teams are building these systems.
So bias is a major one. What else?
Privacy and data security. There's a fundamental tension here. For agents to be effective, especially personalized ones, they often need deep, continuous access to vast amounts of personal or organizational data, emails, calendars, location, financial transactions, health info. This naturally creates risks of pervasive surveillance and incredibly detailed user profiling, far beyond what was possible before. And the black box nature of many complex models makes true informed consent really difficult. Can users fully understand how their data will be used by an agent whose reasoning isn't fully transparent? Plus, as we mentioned, agents centralize sensitive data, making them prime targets for cyber attacks. A breach could lead to catastrophic leaks of highly personal information. There's also the erosion of anonymity. Even if data is anonymized, combining multiple data sets through powerful agents can often re-identify individuals.
That's deeply concerning. And what about jobs? That's always a big topic with AI.
Absolutely. The future of work. Job displacement and augmentation. This is a complex one. AI agents can automate not just repetitive physical tasks, but also complex cognitive workflows previously done by humans. Think paralegals, analysts, customer service reps, even some aspects of coding or writing. This raises the real possibility of significant job displacement across many sectors, potentially affecting millions. The socioeconomic consequences could be severe. Rising unemployment, financial hardship for those displaced, potentially widening wealth inequality, and polarization of the labor market into very high skill and very low skill jobs. Ethically, there's a strong argument for prioritizing augmentation over wholesale replacement, designing systems where AI handles the routine, data intensive parts of a job, freeing up humans to focus on creativity, critical thinking, complex problem solving, empathy, things humans excel at. The human in the loop model. But this also creates an ethical imperative for reskilling and upskilling. Organizations and governments have a responsibility, arguably, to invest heavily in training programs to help people adapt, learn how to manage, collaborate with, and even teach these AI systems effectively. The gains in efficiency shouldn't just benefit capital, they need to be shared equitably, and that requires workforce adaptation.
These issues feel connected. Bias, privacy, job impacts.
They are incredibly interconnected. Think about it. Intrusive data collection, privacy, can feed biased models, fairness, which might then automate jobs in a discriminatory way, future of work. It can become a reinforcing cycle. Perhaps the most profound ethical risk here is the potential to scale systemic injustice at machine speed. A single biased human manager might harm a few people. A biased AI agent deployed globally in hiring or loan applications could institutionalize discrimination affecting millions almost instantly. This makes holistic ethical governance not just ticking compliance boxes for bias or privacy or security, but looking at the whole system and its societal impact absolutely essential. It's not just a best practice anymore, it's arguably a societal necessity for deploying powerful agentic AI responsibly.
Which brings us, I suppose, to the future. Where is all this heading? The evolution of these agents feels like it's pointing towards that ultimate, maybe mythical goal. Artificial general intelligence, AGI?
It certainly feels like a direct path, yes. Current research frontiers in AI agents are very much focused on overcoming today's limitations in ways that build towards more general intelligence. For instance, enhancing reasoning and planning. Researchers are exploring hybrid architectures, combining the pattern-matching strengths of LLMs with the rigorous logic of symbolic AI. They're incorporating formal search algorithms like Monte Carlo tree search, which is key for AlphaGo, to enable more complex, reliable, long-term planning.
So making them better thinkers. What else?
Improving learning and adaptation. The goal is agents that learn continuously, not just from explicit feedback, but also from implicit signals in their interactions. Scaling up reinforcement, learning to handle more diverse tasks and transfer skills learned in one domain to another is a huge focus. We're also seeing major work on advanced memory architectures. Current LLMs have limited context windows. They forget things quickly. So researchers are designing hierarchical memory systems, short-term, long-term, maybe even separate memory for skills or workflows, and dynamic memory augmentation, like retrieval augmented generation, RAG, which allows agents to pull in relevant information from vast external knowledge bases on the fly, overcoming their static training data.
And what about the multi-agent systems we talked about?
That's another key frontier. Sophisticated multi-agent collaboration. Research is pushing for better communication protocols, more robust coordination strategies, exploring heterogeneous MAS, where different agents might even use different underlying LLMs optimized for specific tasks. And interestingly, using MAS itself as a tool to simulate complex systems and understand emergent behavior, drawing inspiration from biology, like ant colony foraging or swarm intelligence.
Okay, so all these advancements are pushing capabilities forward, but just to be clear, what is the definition of AGI we're talking about here?
Right. AGI, artificial general intelligence, is that hypothetical future AI that possesses human-level cognitive abilities across the board. The ability to understand, learn, and apply intelligence to any intellectual task that a human can. It's about broad, flexible, adaptive intelligence, not just excelling at narrow, predefined tasks like current AI does. True general problem-solving ability.
And the idea is of building better and better AI agents is the path to get there.
That's a dominant view, yes. The agentic path to AGI. The argument is that developing increasingly capable autonomous agents, improving their perception, reasoning, planning, learning, interaction, is an incremental process where each step builds foundational components needed for general intelligence. This aligns well with both connectionist approaches, scaling up neural networks, and hybrid approaches. Many leading research organizations explicitly advocate for this gradual, iterative transition towards AGI. The idea is to deploy successively more powerful, yet still constrained and understood, agentic systems. This hopefully allows us to manage the risks and give society time to adapt rather than facing a sudden, potentially disruptive arrival of superintelligence.
Here's maybe a provocative thought then, building on the MES idea. Could AGI not be a single monolithic superbrain, but an emergent property? What if AGI emerges from a sufficiently complex and dynamic system of interacting specialized agents, much like human intelligence seems to be a combination of specialized brain modules and the collecting intelligence of society?
That's a very compelling perspective, and one gaining traction. It shifts the focus significantly. The research challenge becomes less about how do we build one vastly superior model, and more about how do we design the right system of interaction, coordination, collective learning, and knowledge sharing among many agents. Human society achieves incredible things through distributed cognition. Maybe digital general intelligence will look similar. But this also has profound safety implications. Aligning a single superintelligence is hard enough to conceptualize. Aligning a vast, distributed, constantly evolving digital society of agents, that's a monumental challenge, perhaps the critical challenge for ensuring a beneficial future with advanced AI.
Wow. Okay, we have covered a lot of ground today. We've journeyed through this really complex and fast-moving world of artificial intelligence agents. We went from their basic principles, how they're designed using frameworks like PEAS, explore the different types, the tech stack powering them, all the way to multi-agent systems, real-world applications, and those critical challenges and ethical considerations. We've really seen them as these active, autonomous entities driven fundamentally by that sense, think, and act cycle.
Absolutely. And a key thing to remember, I think, is that effective intelligence, whether artificial or natural, seems intrinsically tied to an agent's interaction with its specific world. It's embodied, grounded, and always keep in mind those inherent trade-offs, performance versus predictability, autonomy versus control. And that concept you raise, agentic debt, I think that's vital. It highlights the ongoing need for robust governance and responsible management as these systems become more powerful and widespread.
So, thinking about you, our listener, what does all this really mean for you? It feels like in this increasingly agentic world, our roles might be fundamentally shifting. Maybe we move from being the primary doers of many tasks to becoming the governors, the overseers, the designers of the goals and guardrails for these complex autonomous systems. Perhaps the most critical human skill moving forward won't be task execution, but the wisdom to design, configure, monitor, and continuously refine these governance frameworks, ensuring agents act effectively, safely, and aligned with human values. Consider those implications of computational management science. How might we interact with or even manage virtual companies run by specialized agents? It sounds like science fiction, but it might be closer than we think. Definitely something to mull over.